Welcome back, guys. We're going to continue with solving circular motion problems. So two artificial satellites, 1 and 2, orbit the Earth in circular orbits having radii r1 and r2, respectively as shown above. If r2 equals 2 times r1, the acceleration a2 and a1 of the two satellites are related by which of the following? All right, so let's try to get a relationship between the radiuses and the acceleration. So we know that, oh, that is way too thick. F net is equal to mv squared over r. I know that this is my acceleration. So I'm going to rewrite this as F net equals m a1. All right, so what is this force on mass 1? It is mg over r1 squared. So that's going to be equal to ma. So I'm going to cancel out that. All right, so the same way I did this with the first one, I'm going to do it with the second one. And say that's my second acceleration. So again, F net is going to be equal to ma2. And then I'm going to have gm over r2 squared equals a2. All right, so the other thing that we know is that r2 is equal to 2r1. So I'm going to put in 2r1 for r2. And that's squared. And so what I end up with, erase this just to get it out of the way, is that a1 is gm over r1 squared, and a2 is gm over 4 r1 squared. So that would tell me that a2 is 1/4 of a1. All right, I'm going to erase this and move on. A newly discovered planet, Cosmo, has a mass that is 4 times the mass of the Earth. The radius of the Earth is re. The gravitational field strength of the surface of Cosmo is equal to that of the surface of the Earth if the radius of the Cosmo is equal to. All right, so our formula is gravitational field strength is the same as acceleration due to gravity. So this is going to be gm over r squared. That's what they're saying when they're saying gravitational field strength. I want it to stay the same. If I am putting my mass by 4, what do I have to do to r? So this is equal to this. I need the radius to be twice, because 2 squared would be 4. Now I'd have 4 over 4, which would be 1. All right, a mass m moves on a curved path from point x to point y. Which of the following diagrams indicates a possible combination of the net force on the mass, the velocity, and the acceleration at the location shown? All right, so we know that at the moment, any moment, that our force and our acceleration have to agree. So force and acceleration don't agree, don't agree, don't agree. And then we also know when it's curving, when we have circular motion, that we have to have a centripetal force, a force directed towards the center. This is curving here. This force is not directed towards the center. Now looking at D, D is also not directed completely towards the center, but it does have a component that's towards the center. There would be part of the force that's towards the center, part of the force that's up, so it must be turning and accelerating both. The radius of Earth is approximately 6,000 kilometers. The acceleration of an astronaut in a perfectly circular orbit 300 kilometers above the Earth would be most likely. So you would expect, if you were further away from the center of the Earth, for the acceleration to go down. You wouldn't expect it to go down by much, because compared to 6,000, 300 is not much. So I would expect that to be like 9. No math for that one. A satellite moves in a stable circular orbit with the speed v naught at a distance r from the center of a planet. For this satellite to move in a stable circular orbit at a distance 2r from the center of the planet, the speed of the satellite must be. Okay, so again, F net equals mv naught squared over r. So G m m over r squared equals m v naught squared over r. I can cancel out an r. I can cancel out a little m. I want an expression in terms of v, so I'm going to get v naught by itself, and I'm going to say that v naught is related to gm over r square rooted. So what am I doing? I'm not changing the gravitational constant. I'm not changing the mass of the planet, but I'm making the distance from it from 1 to 2. And so now I have 1 over 2. And so that tells me that I would have to multiply my v naught by 1 over radical 2 to get it to equate. This one has angular velocity in it, which is this lowercase omega. Angular velocity is just equal to our linear velocity times r, as long as, I take that back, our linear velocity divided by r, as long as there's no slipping. So you can just think of it as velocity here. You have an ant that is clinging to a flywheel. The flywheel rotates clockwise with constant angular velocity, so constant velocity. As the wheel rotates, the ant revolves around. The ant can adhere to the wheel with the force much greater than its own weight. It'll be most difficult for the ant to adhere to the wheel as it revolves past which of the 4 points. It's going to be hardest for the ant when he's upside down, because he's going to have to both hold on and counteract all of his weight. And his holding on is going to have to be more than his weight, because it is also going to have to turn him, which is an acceleration. A newly discovered planet has twice the mass of the Earth, but the acceleration due to gravity on the new planet's surface is exactly the same as the acceleration due to gravity on the Earth's surface. The radius of the new planet in terms of radius of r is, so again, we're saying acceleration due to gravity is gm over r squared. We're saying that it's staying the same. So I have gm over r squared, but it has twice the mass. So what do I have to do to this fraction so that I can cancel out the 2? I'm going to have to put a radical 2 in there, because radical 2 squared would be 2, and that would just give me C. A satellite of mass m moves in a circular orbit of radius R with constant speed v. True statements about this satellite include which of the following? That is the definition of all of them. We haven't covered angular speed yet, but like I said, it's the velocity divided by r. Its tangential acceleration is 0 because its speed isn't changing. It's not speeding up or slowing down. And the magnitude of its triple acceleration is also constant because its radius isn't changing, nor is its speed changing. Now, the direction of it's always changing, but so that's going to be all of them. A spring has a force constant of 100 newtons per meter and an unstretched length of 0.07 meters. One end is attached to a post that is free to rotate in the center of a smooth table, as shown in the top view above. The other end is attached to a 1 kilogram disc moving in uniform circular motion on a table, which stretches the spring by 0.03 meters. Friction is negligible. What is the centripetal force on the disc? So when it's at this, and you're looking down on it, so the gravity's not in it. So if we were talking like normal, it would be coming out of the board, and weight would be going in. And so the force that is keeping it going in circle is the spring force, the restoring force from Hooke's law. And so you're going to say that this is your centripetal force. Well, we know this is equal to kx. So our k is 10 newtons per meter. This should be around the x and not the k. And we're saying that it stretches by 0.03 meters. And so this would be 3 newtons. Figure of a dancer on a music box moves counterclockwise at a constant speed around the path as shown above. The path is such that the lengths of its segments, PQ, QR, RS, and SP are equal. Arcs QR and SP are semicircles. Which of the following best represents the magnitude of the dancer's acceleration? All right, so if it's moving at a constant speed, it's only going to accelerate when its direction is changing. And so that's going to be from Q to R and from S to P. So these would both be centripetal accelerations, and they would be constant. That's supposed to be like a half circle there. And so we start at P. So P to Q is nothing, so that one doesn't work. That doesn't work. And then as soon as it gets to Q, it's going to immediately be that acceleration. And so this is going to be v squared over r. The r is constant and the speed is constant. Then we get to r, it's going to be nothing. And then we get back to s, it's going to be v squared over r.